This $2.0 PVC pipe builds a free power generator any retiree can finish in 1 weekend. But here is what the videos do not tell you. The moment you finish bolting that turbine together and mount it on your roof, you will face a choice that nobody talks about. Not the solar companies, not the energy independence websites, not even the other retirees doing this in their backyards. That choice, frankly, has more to do with whether your generator actually saves you money than the pipe itself does. And I will explain exactly what it is before this video ends. Stay with me, because this detail is the difference between a weekend project that cuts your bill and one that sits on your roof generating nothing but regret. The average American household now spends about $150 a month on electricity. For someone on a fixed income, retirement income especially, that is not a small number. Over a year, it is $1,800. Over 10 years, with inflation climbing the way it has, you could be looking at $25,000 or more just to keep the lights on. That math is what sends people to YouTube at 2 in the morning searching for alternatives, and they find the PVC turbine. They see the price tag, $20 for materials, sometimes less if you salvage the motor, and something clicks. This could work. This could actually work. But let me ask you something directly. If you subscribe to this channel, it is probably because you are tired of being told what to do with your money by people who do not understand what retirement really means. You earned that income. You planned for it. And now you are supposed to let a utility company take 30, 40, sometimes 50% of it before you even get to choose what you do with what is left. That anger, that sense of injustice, that is real, and it is exactly what I want to talk to you about today. If you have not already, subscribe to the channel right now. And if you have built something like this, or if you are thinking about it, I want you to leave a comment below telling me your story. What broke the camel's back for you? Was it a single bill, or was it the pattern? I read every comment, and the ones from people who have actually tried this, they teach me things I cannot learn any other way. Wait, I need to pause here for a second because there is something critical about this that most people get wrong from the beginning. Before you cut a single inch of PVC, before you order a motor or touch any tool, you need to understand one specific factor about your property that will determine whether this entire project makes sense for you. Not whether it is possible, whether it actually works. And this is explained in depth, along with the full mechanical blueprints and the testing data from real setups in real neighborhoods, in our complete guide on DIY wind generation. That guide is in the description and pinned to the top of the comments. It is not free, because it is written by people who have actually built these systems and measured what they produce over months and years, not weeks. It cuts through the hype and tells you exactly what these generators do and do not do. The core reason this matters is something called wind exposure. Not wind in general, wind exposure. Your specific property, that exact roof line, that angle, that height, that clearing, or lack of it, around your house. A PVC Savonius turbine is not like a solar panel. With solar, the physics is straightforward. A panel produces electricity when sunlight hits it. Roughly the same output everywhere in the continental United States if you adjust for latitude and seasonal tilt. But wind is different, completely different. Wind accelerates and slows depending on terrain. A house at the bottom of a hill, surrounded by trees, gets maybe 40% of the wind that a house on an open ridge receives. Same neighborhood, same postal code, 40%. That is not a small difference. That is the difference between 800 kilowatt hours per year and 1500. The difference between cutting your bill by 20% and cutting it by half. And this is where the choice I mentioned at the beginning comes in. When you are standing in your backyard, looking up at your roof line, you have to ask yourself the honest question. Does my property actually have wind exposure? Or am I building this because I want to, because the idea feels right, because I am tired of paying the utility company and that emotion is overriding the engineering? Both are valid, but only one of them will save you money. Part 1 ends here. Honestly, this is the part that still bothers me. I have watched people invest $2,000 in materials and labor, only to realize 6 months later that their property sits in a wind shadow. The turbine spins, sure, but it barely moves. They get frustrated, they abandon it, and nobody talks about this failure rate because it is inconvenient for the solar industry, which dominates the energy independence narrative entirely. Before we continue, and I mean really continue, keep this in mind for a second. The mechanics of building your turbine are straightforward. The physics is old, proven, simple. But knowing whether your property can actually support this build is where most people stumble. This is exactly the kind of technical foundation work that our complete guide covers in depth. You will find the step-by-step process for measuring your wind exposure, understanding microclimates, and calculating realistic power output. That guide, that ebook, is in the description and pinned to the top of the comments. It costs money because it is real work, real data. Not padding. Worth every penny if you are serious about this. 3 tools will tell you what you actually need to know. First, a simple anemometer. Not the fancy $500 weather station. A handheld wind meter. $20 to $30 online. You hold it steady at the height where your rotor will spin and record the readings every hour for at least 2 weeks. Morning, noon, evening, overnight. Different wind patterns emerge at different times of day. A calm afternoon does not tell you anything useful. What matters is whether your property consistently sees 7 miles per hour or higher. Second, use the National Wind Resource Assessment Maps. The Department of Energy publishes wind speed data by county, and you can cross-reference your exact location. Do not rely on national averages. Your county might sit in a wind corridor while your specific neighborhood is sheltered. 3 miles difference in latitude can change your annual wind speed by a full mile per hour. That sounds small. Over a year, it compounds into real money. Third, spend an afternoon looking at your actual surroundings. Topography matters more than most people admit. If your house sits in a valley, the surrounding hills funnel wind away from you. If you are on a slope or a ridge, you catch more wind than your neighbors 500 yards down. Trees are complicated. A few scattered oaks around your property actually help by speeding up air movement at ground level. A dense forest surrounding you kills the wind entirely. Look at how existing trees move in wind. Do branches bend? Do leaves rustle hard? Or is it just a whisper? That visual tells you something real. So now you have real numbers, your anemometer readings, your Department of Energy data, your honest assessment of your property's position and shelter. You take those 3 pieces of information and you run a quick calculation. Most people skip this. They just build. That is how you end up with expensive lawn decoration that generates 30 watts on a windy day. Here is how the math actually works. The power output of a Savonius rotor depends on 3 variables: wind speed, rotor diameter, and the drag coefficient of your specific design. The relationship is not linear. Power output increases with the cube of wind speed. That means if your property averages 9 miles per hour, you generate almost 3 times the power of a property that averages 7. Same turbine, different location, 3 times the electricity. A 2-foot diameter rotor in consistent wind sits right around the baseline for actual useful generation. 1,200 to 1,800 kilowatt hours per year at a good location. That will cut your summer cooling costs and offset a meaningful chunk of winter heating if you have electric heat. A 3-foot rotor pushes you closer to 3,000 kilowatt hours annually. You start looking at genuinely replacing utility power. The real question is whether your wind exposure justifies the build, and frankly, if your anemometer averages below 7 miles per hour, it does not. You will spend $300 in materials and 100 hours in labor to generate what you could have built in solar capacity for the same money. But if your anemometer reads above 7 consistently, and especially if it averages in the 8 to 12 range, then you have something worth building. Here is where most people stop. They look at that number, 7, 8, maybe 9 miles per hour, and they think, that is not a lot of wind. But wind speed compounds. A turbine in 9 mile per hour average conditions generates roughly 3 times the power of one in a 5 mile per hour average. That is not a linear relationship. It is cubic. The math does not forgive weak wind sites, and it will not let you fake it either. Your best friend here is honesty. If you live in a sheltered valley, surrounded by trees, tucked into a suburban neighborhood where fences and houses break the flow, that anemometer will tell you the truth before you waste a single weekend. And I respect that. Some people read that data and walk away. They switch to solar with confidence. They know why they made that choice. That is not a failure. That is wisdom. But some of you will open that anemometer log and see 7.5, 8, 9, or higher. Your site has actual wind resource. Your location is not perfect, but it is viable. For those people, the conversation changes completely. Building a functional rotor takes 1 afternoon, 2 hours if you have a jigsaw and a drill. Bolting it to a salvaged motor, and yes, you will salvage a motor, takes another 3 hours. Your materials cost somewhere between $60 and $120, depending on whether you are scavenging locally or ordering online. The motor is the variable. A treadmill motor salvaged from a curb pick is free. A used permanent magnet motor from an industrial supply site runs $30 to $40. A new one climbs to $80 or $100. The physics, though. The physics is what makes this worth your time. When wind strikes the curved face of a PVC blade, it does not push evenly. The pressure concentrates on the concave or scooped out side. The convex or rounded back catches less drag. That difference, that asymmetry, creates torque. The wind pushes one blade while sliding around the back of the other. The rotor turns. Continuous turn. No gearbox needed. No complex pitch control needed. Vertical axis machines do not care which direction the wind comes from. A gust from the north works the same as one from the southwest. Horizontal axis turbines, the kind with propeller blades, they need to yaw, meaning rotate the entire head to face the wind direction. They need tail fins or electronic motors to do that tracking. A Savonius rotor just spins. Wind, from any angle, produces torque. That simplicity is part of why utility companies and solar installers do not talk about it. Before we continue, I need you to understand something critical here. The mechanisms that make these rotors work, the specific calculations for your wind site, the detailed wiring diagrams for connecting your motor to a charge controller, all of that sits in our in-depth guide. It is available in the description and pinned at the top of the comments. That guide walks you through the engineering signals that separate a viable site from a waste of time. It is the resource you come back to when you are at the workbench with a part in your hand and a question in your head. Not free, but absolutely worth it for anyone serious about this build. The practical side is simpler than you might expect. Your rotor connects to a shaft. That shaft sits on 2 bearings. Skateboard bearings work, or pillow block bearings if you want something rated for continuous duty. The shaft connects to your motor. The motor produces direct current. That DC current flows into a charge controller, the same kind you would use for a solar panel. The charge controller protects your batteries and regulates the incoming voltage. Your batteries store it. An inverter converts it to household current when you need it. Sound familiar? It should. The rest of your system is already designed for this. You are not learning a new architecture. You are adding a second-generation source to an existing setup. The mounting location matters more than most people realize. You want the rotor at least 10 feet above ground level, and higher is better. Wind speed increases with altitude. At 30 feet, you are seeing wind speeds roughly twice what you measure at ground level. But not everyone can install a 30-foot tower. Most backyard builds sit in the 15 to 20-foot range. Even that height pulls you out of the ground friction zone, where wind slows down. A rotor at 15 feet, spinning in a 9-mile-per-hour average wind site, will generate somewhere between 400 and 600 kilowatt-hours annually. Add a second rotor, either stacked on the same tower or on a separate tower 20 feet away, and you double that, 600 to 1200 kilowatt-hours per year from 2 turbines. Add solar panels for daylight generation, and suddenly you are looking at genuine grid independence. Not someday. Not if the math works out. Now. The bolt pattern matters as much as the height. Loose fasteners will vibrate themselves free in weeks. Tight fasteners, properly spaced, keep the rotor balanced and spinning true. You are not building a showpiece. You are building a machine that has to survive wind gusts, temperature swings, and months of continuous operation. Frankly, this is the part that still bothers me about most online tutorials. They show you how to cut and assemble, but they skip over the boring reality. Maintenance. A wind turbine that sits untended does not stay a wind turbine for long. You need to inspect the blade connections every 3 months. Check the bearing alignment twice a year. Keep the motor windings dry. A rusted bearing or a corroded wire connection will kill your output faster than bad wind. The good news is that maintenance on a PVC turbine takes maybe 30 minutes per visit. You climb the ladder, or you use a pulley system if climbing becomes difficult, and you walk through a simple checklist. No specialized tools, no electrician required, just your eyes and a wrench. Now, here is where the math shifts. A single rotor generates somewhere between 400 and 600 kilowatt hours per year if you live in a 9 mile per hour average wind location. Most of the United States falls into that category, whether you are on the East Coast, the Midwest, or even parts of the South. You might not be in a mountain pass or on a ridgeline, but you probably have usable wind. Double the rotors, and you double the output. That moves you from seasonal supplementation to actual grid independence. Instead of cutting your bill in half, you eliminate it. Instead of running your backup generator twice a year, you might never run it at all. The layering works too. Solar panels during the day, wind turbines at night and in winter. Cloudy February morning, the turbine is still spinning. Calm summer evening, your panels built up a battery charge all afternoon. Together, they cover gaps that neither one covers alone. Most people calculate their power needs and then stop. They say, I use 2,000 kilowatt hours per year, so I need enough solar and wind to cover that. That math is correct, but the application is not. You do not need to generate 2,000 kilowatt hours spread evenly across 12 months. You need to generate enough in your worst season to cover that season, while building reserves in your best season. Winter wind is often stronger than summer wind. Summer sun is more abundant than winter sun. A hybrid system naturally corrects for these swings. That is why the rotor exists in the first place, not as a secondary add-on, but as a primary component of a real off-grid strategy. Now, before we continue with the final details, I need you to think about something carefully. This is a kind of decision that looks simple on the surface, but has real complexity underneath. Before you commit to building even one turbine, you need to understand the full picture of your site and your consumption. That is where the complete guide we have in the description becomes invaluable. It walks you through the site assessment process, how to measure your actual wind resource, how to download publicly available wind maps, how to overlay that against your real monthly power usage. It explains the signals and patterns that separate a site that will work from one that will waste your time and money. Many of you are watching this and thinking, my property is flat and suburban. There is no wind here. That assumption costs people thousands of dollars every year because they believe it without checking. Flat suburban land can have excellent wind if it sits in the path of prevailing wind patterns or if it is positioned away from large obstructions. A simple anemometer, a wind measurement device, costs $30. Duct tape it to a PVC pole, measure for 2 weeks, and you know your actual wind speed. Not a guess. Not a weather forecast. Your real site data. The guide breaks down how to read that data, where to find historical wind records for your county, and how to compare your site against known good locations. It shows you the patterns that indicate a viable wind installation versus wishful thinking. That is the difference between success and wasted materials. So you measure 2 weeks of actual data beats 2 years of assumptions. Write down the readings. Morning, afternoon, evening. Different seasons matter. Winter wind is not summer wind. Spring can surprise you. Most people skip this step entirely, and that is precisely why they fail. Once you have the numbers, you are comparing your site against what the reference guide calls the wind resource map for your region. The National Renewable Energy Laboratory publishes county-by-county data going back decades. Free, public, sitting online. Your measurements either confirm that data or they contradict it. If they contradict it, you have found something valuable, a microclimate advantage that the maps missed. That is when you move to the second question, tower height. A PVC Savonus turbine works best when the rotor sits between 12 and 25 feet above ground level. Not on your roof, not tucked behind trees. Up, in the clear, where wind accelerates and flows unobstructed. Height multiplies power output. The relationship is not linear. Doubling your tower height does not double your power. It triples it or better, depending on wind shear in your area. That is a physics principle called the wind shear exponent, and it means every foot you gain matters enormously. But here is where most DIY builders make a critical mistake. They build a tower that is strong enough to hold the turbine. They do not build a tower that can survive a sustained ice storm. They do not account for the lateral load when wind gusts from an unexpected direction. They do not calculate the cyclic stress of 10,000 hours of vibration. Your tower materials cost $40 to $80. Your turbine costs $20. The engineering of the tower, the guying system, the foundation, the bracing, that is what separates a working installation from a collapses in the first winter installation. Before we continue, I need to make sure you understand something important. Everything I am explaining here, the tower calculations, the load analysis, the wind shear coefficients, the foundation engineering that keeps your turbine from becoming a dangerous projectile, all of it is covered in detail in the complete guide available in the description and pinned comment below. This ebook walks you through the design principles that engineers use to build commercial wind systems, then shows you how to apply them to a PVC build on a budget. It is not free, it is a paid resource, and it exists because this information is too important to abbreviate. The guide gives you the signals, the specific measurements and safety thresholds that tell you whether your tower design is sound or dangerous. Many builders skip this phase. They think a tower is a tower. It is not. A tower engineered for 35 mph winds is not engineered for 50 mph winds. One is adequate, the other is disaster waiting for weather. Your foundation anchors everything: concrete, rebar, auger screws sunk 3 feet into the ground. This is not something you improvise. A 40-pound turbine at 30 feet becomes a 3,000-pound force in a storm. Your foundation has to arrest that force without moving. Concrete alone is not enough if your soil is soft clay or sandy loam. You add anchors, you add bracing, you add cost. Most people budget $200 for a complete wind turbine setup. That includes the turbine itself. They end up spending half of that on a tower that will not last 2 seasons. Then they blame the concept instead of their execution. The margin between success and failure is not the turbine. The turbine is the easy part. The margin is the infrastructure that holds it up and the engineering that made sure it will not kill anyone when the wind gusts to 50 mph on a Tuesday night in March. That is the signal that separates builders who are still generating power 5 years later from builders who are replacing fallen towers or buying grid power again because they gave up. It is not luck. It is not magic. It is attention to engineering. And that is where we arrive at the revelation I promised you at the beginning of this video. The reason your utility company, your solar installer, and every federal rebate program stays silent about the Savonius turbine is not because it does not work. It works. Wind turbines have been catching air for over a century. The reason is structural, economic, and deliberate. A solar panel company sells you hardware. They sell you panels, inverters, batteries, monitoring systems. Every component has a profit margin. Every failure creates a repeat sale. A wind turbine, once it is built and installed, generates power for 20, 30, sometimes 40 years with minimal intervention. One purchase, one transaction. Then you are free. The rebate system, the tax credits, the state incentive programs, they are all designed to move hardware through the supply chain. Volume, replacement cycles, upgrades. A turbine that works quietly on your property for 3 decades, requiring only occasional maintenance and a watchful eye, generates almost no secondary revenue. It is not in anyone's interest to tell you about it. Your utility wants you on the grid. Your installer wants you buying panels. The financing company wants you in a loan for 15 years. The replacement cycle wants you upgrading batteries every 7 years. And the entire system works, because nobody has to tell you this is happening. It just does, quietly. Why you are paying your bills? A $20 piece of PVC pipe, a salvaged motor, some bolts, and a tower you can engineer yourself does not fit into that model. It breaks it. That is why you have never heard of it. Not because it fails, because it succeeds too well. Now, if you are sitting here thinking, I have waited this long, I might as well just go solar. I understand that impulse. Solar is visible. It is marketed. You know what you are getting. But consider this. You live somewhere with winter. You live somewhere with night. You live somewhere with clouds and seasons that change. A turbine does not care about any of that. When the sun sets, the turbine keeps working. When winter storms arrive, when the temperature drops and the utility companies strain under peak demand, your turbine is generating power at the moment you need it most. The math does not lie. A $1,500 wind turbine installation, materials, tower, engineering, labor if you hire someone for the foundation, will outlast 2 solar panel systems. It will generate electricity when solar cannot. It will do it with almost no degradation. And it will do it while your utility company, your power company, and every energy corporation that benefits from your dependence stays completely silent about the fact that you could be doing it. Your fixed income does not have to shrink every year. Your bills do not have to climb, and you do not have to wait for permission from an installer, a rebate program, or a utility company to take back control of your energy costs. This is your moment. You have the knowledge. You have the materials within reach. You have the infrastructure, the tools, the skills, the determination that built this country. What you needed was the understanding of why nobody was telling you about this option. Now you have that too. Take one afternoon this month. Gather your materials. Build your first small turbine. Test it on your property. See what the wind can actually do when you give it a shape to work with. That is all it takes to begin. Not a loan, not a 15-year commitment. Just one weekend, $20, and the decision to trust your own hands instead of waiting for someone else's permission. Thank you for watching. If this video sparked something for you, subscribe to the channel and leave a comment telling me about your own experience with alternative energy or whether you are planning to build your first turbine soon. Ring that notification bell so you never miss a new upload, and we will see you next time.